The human body is constantly exposed to a myriad of pathogens, including bacteria and viruses, which can cause a range of infections and diseases. Despite these threats, most of us remain healthy thanks to our immune system, a complex network of cells, tissues, and organs that work together to defend the body against harmful invaders. Understanding how the immune system functions is crucial to appreciating its role in maintaining health and combating infections. This guide delves into the fascinating world of the immune system, exploring its mechanisms, responses, and the ways it protects us from bacterial and viral infections. We will cover the following key areas. Understanding the immune system. The immune system is our body's defense mechanism against harmful invaders like bacteria, viruses, and other pathogens. It's a complex network of cells, tissues, and organs that work together to protect the body from infections and diseases. Let's dive into the fundamental components and functions of this incredible system. Introduction to the immune system. The immune system can be thought of as an army with different branches working together to keep us healthy. It has two main parts: the innate immune system and the adaptive immune system. Innate immune system. This is the body's first line of defense and responds quickly to infections. It includes physical barriers like skin and mucous membranes, as well as immune cells that attack invaders. Adaptive immune system. This part of the immune system develops more slowly but provides a targeted response to specific pathogens. It has the ability to remember past infections and respond more effectively in the future. Key components of the immune system. Several components work together to form the immune system. White blood cells, WBCs, also known as leukocytes. These cells are the soldiers of the immune system. There are several types of WBCs, each with a specific role. Neutrophils. These are the first responders to infection. They move to the site of infection and attack and digest bacteria and fungi. Lymphocytes. These include B cells and T cells. B cells produce antibodies, while T cells destroy infected cells and coordinate the immune response. Macrophages. These cells act like scavengers, engulfing and digesting pathogens and dead cells. Antibodies. These are proteins produced by B cells that recognize and neutralize foreign invaders. Each antibody is specific to a particular antigen, a substance on the surface of pathogens. The lymphatic system. This system includes lymph nodes, lymph vessels, and lymph fluid. It helps transport immune cells throughout the body and filters out harmful substances. The spleen. This organ filters the blood, removing old or damaged blood cells and pathogens. The thymus. This small organ is where T cells mature and become capable of recognizing and attacking pathogens. Bone marrow. This is the spongy tissue inside bones where new blood cells, including WBCs, are produced. How the immune system detects invaders. The immune system relies on its ability to distinguish between the body's own cells and foreign cells. This is achieved through antigens, which are molecules found on the surface of pathogens. When the immune system detects an antigen, it triggers an immune response. Pattern recognition receptors, PRRs. These receptors on immune cells recognize common patterns on pathogens, known as pathogen-associated molecular patterns, PAMPs, and initiate the immune response. Antigen presentation. When immune cells like macrophages and dendritic cells engulf a pathogen, they break it down and present pieces of the pathogen, antigens, on their surface. This process is essential for activating T cells. The role of inflammation. Inflammation is one of the first responses of the immune system to infection or injury. It helps isolate the affected area, preventing the spread of pathogens, and recruits immune cells to the site. The main signs of inflammation are redness, heat, swelling, and pain. Vasodilation. Blood vessels widen, increasing blood flow to the affected area, which causes redness and heat. Increased permeability. Blood vessel walls become more permeable, allowing immune cells and proteins to move into the tissue, which leads to swelling. Pain. Chemicals released during inflammation stimulate nerve endings, causing pain. The adaptive immune response. If the innate immune response is not sufficient to eliminate the pathogen, the adaptive immune system steps in. This response is more specific and involves the activation of lymphocytes. B cells and antibodies. When B cells encounter their specific antigen, they become activated and differentiate into plasma cells, which produce large quantities of antibodies. These antibodies bind to the antigen, neutralizing the pathogen and marking it for destruction by other immune cells. T cells. There are two main types of T cells. Helper T cells. These cells do not kill pathogens directly. Instead, they help activate other immune cells, including B cells and cytotoxic T cells. Cytotoxic T cells. These cells directly kill infected cells by recognizing and binding to antigens presented on the surface of these cells. Memory and immunity. One of the most remarkable features of the adaptive immune system is its ability to remember past infections. After an infection is cleared, some B and T cells become memory cells. These cells remain in the body for years, ready to respond quickly if the same pathogen is encountered again. This memory response is the basis for long-term immunity and is the principle behind vaccinations. The immune system is a complex and highly organized defense network that protects us from a wide variety of pathogens. Understanding the components and functions of this system is crucial for appreciating how our bodies maintain health and fight infections. In the next chapters, we will delve deeper into how the immune system responds specifically to bacterial and viral infections, the role of vaccinations, and ways to keep our immune system strong. How the immune system responds to bacterial infections. Bacteria are single-celled organisms that can cause a wide range of infections in the human body. While many bacteria are harmless or even beneficial, some can lead to serious diseases. Understanding how the immune system responds to bacterial infections is crucial for appreciating the body's defense mechanisms. What are bacterial infections? Bacteria are microscopic organisms that come in various shapes, such as rods, spheres, and spirals. They can be found almost everywhere, including in soil, water, and inside our bodies. While many bacteria are beneficial, such as those in our gut that aid in digestion, pathogenic bacteria can cause infections. Common bacterial infections include strep throat, tuberculosis, and urinary tract infections. The body's initial response to bacteria. When bacteria enter the body, the immune system detects them through their antigens, specific molecules on the surface of bacteria that trigger an immune response. The first line of defense includes physical barriers and the innate immune system. Physical barriers. The skin and mucous membranes act as physical barriers to prevent bacteria from entering the body. When these barriers are breached, the innate immune response kicks in. Innate immune response. This response is the body's immediate reaction to infection. It includes inflammation, phagocytosis, and the activation of various immune cells. Inflammation. The immediate response. Inflammation is one of the first responses to a bacterial infection. It involves the following steps. Vasodilation. Blood vessels near the infection site widen, increasing blood flow. This causes redness and heat. Increased permeability. Blood vessel walls become more permeable, allowing immune cells and proteins to enter the affected tissue. This leads to swelling. Pain. Chemicals released during inflammation stimulate nerve endings, causing pain. This serves as a signal to the body to rest and protect the affected area. Phagocytosis. Engulfing the invaders. Phagocytosis is the process by which certain immune cells engulf and digest bacteria. The main phagocytic cells are neutrophils and macrophages. Neutrophils. These cells are the first to arrive at the infection site. They rapidly engulf and destroy bacteria. Macrophages. These larger cells act as scavengers, engulfing and digesting bacteria, dead cells, and debris. They also play a crucial role in alerting the adaptive immune system by presenting antigens from the digested bacteria. The role of the adaptive immune system. If the innate immune response is insufficient to clear the infection, the adaptive immune system takes over. This response is more specific and involves the activation of lymphocytes, B cells and T cells. Activation of B cells. When B cells encounter their specific antigen, they become activated and differentiate into plasma cells, which produce antibodies. These antibodies bind to the bacteria, neutralizing them and marking them for destruction by other immune cells. T cells. Helper T cells assist in activating B cells and other immune cells, while cytotoxic T cells destroy infected cells. Antibodies and their role. Antibodies, or immunoglobulins, are proteins produced by B cells. They play a crucial role in the immune response to bacterial infections. Here's how they work. Neutralization. Antibodies bind to bacterial toxins, neutralizing their harmful effects. Opsonization. Antibodies coat the surface of bacteria, making it easier for phagocytic cells to engulf and destroy them. Complement activation. Antibodies trigger the complement system. a series of proteins that enhance the immune response by promoting inflammation and assisting in the destruction of bacteria. Formation of memory cells. After an infection is cleared, some B and T cells become memory cells. These cells remain in the body for years, ready to respond quickly if the same bacteria are encountered again. This memory response is faster and more efficient, providing long-term immunity against specific bacterial infections. Examples of bacterial infections and immune response. Let's look at how the immune system responds to two common bacterial infections. Streptococcal pharyngitis, strep throat. Initial response. The infection begins in the throat, causing inflammation and pain. Phagocytosis. Neutrophils and macrophages engulf the bacteria. Adaptive response. B cells produce antibodies against the streptococcal antigens. Helper T cells assist in activating other immune cells. Memory formation. Memory B and T cells are formed, providing immunity against future strep throat infections. Tuberculosis. Initial response. The bacteria infect the lungs, causing a localized immune response. Phagocytosis. Macrophages engulf the bacteria but struggle to destroy them due to the bacteria's ability to survive within the cells. Adaptive response. T cells play a crucial role in controlling the infection. They recognize infected macrophages and help contain the bacteria. Memory formation. Memory T cells are formed, providing long-term immunity, although tuberculosis can persist in a dormant state and reactivate later. The immune system's response to bacterial infections is a complex and highly coordinated process involving both the innate and adaptive immune systems. From the initial detection of bacteria to the activation of immune cells and the production of antibodies, every step is crucial for effectively combating infections. Understanding these mechanisms helps us appreciate the incredible efficiency and adaptability of our immune system in protecting us from harmful bacteria. In the next chapter, we will explore how the immune system responds to viral infections, which present a different set of challenges for the body. How the immune system responds to viral infections. Viruses are much smaller than bacteria and present unique challenges to the immune system. Unlike bacteria, viruses cannot replicate on their own. They must invade host cells and hijack the cellular machinery to produce more viruses. This chapter explores how the immune system detects and responds to viral infections. What are viral infections? Viruses are tiny infectious agents consisting of genetic material, DNA or RNA, enclosed in a protein coat. Some viruses also have an outer lipid envelope. Common viral infections include the flu, common cold, HIV, and COVID-19. The body's initial response to viruses. When viruses enter the body, the immune system detects them through their antigens. These are specific molecules on the virus's surface that trigger an immune response. The response involves both the innate and adaptive immune systems. Physical barriers. The skin and mucous membranes act as physical barriers, preventing many viruses from entering the body. When these barriers are breached, the innate immune response is activated. Innate immune response. This immediate response involves several components, including interferons, natural killer, NK, cells, and the complement system. Interferons, the body's first line of defense. Interferons are proteins produced by virus-infected cells. They serve as an alarm system, signaling nearby cells to heighten their antiviral defenses and inhibit viral replication. Types of interferons. There are three main types: type 1, including alpha and beta interferons, type 2, gamma interferons, and type 3, lambda interferons. Functions of interferons. Interferons induce the production of antiviral proteins, increase the visibility of infected cells to immune cells, and enhance the activity of NK cells and macrophages. Natural killer, NK cells. NK cells are a type of lymphocyte that plays a crucial role in the innate immune response to viral infections. They can recognize and destroy virus-infected cells without the need for prior sensitization to the virus. Mechanism of action. NK cells detect changes in the surface molecules of infected cells. They release cytotoxic granules that induce apoptosis, programmed cell death, in the infected cells. Regulation of NK cells. NK cells are regulated by a balance of activating and inhibitory signals. Healthy cells send inhibitory signals to prevent NK cell activity, while infected or stressed cells send activating signals that trigger NK cell action. The adaptive immune response. If the innate immune response is insufficient to eliminate the virus, the adaptive immune system takes over. This response is more specific and involves the activation of lymphocytes, B cells and T cells. Activation of B cells. When B cells encounter their specific antigen, they become activated and differentiate into plasma cells, which produce antibodies. These antibodies can neutralize the virus by binding to it and preventing it from entering host cells. T cells. There are two main types of T cells involved in the adaptive immune response to viruses. Helper T cells, CD4+. These cells help activate B cells and other immune cells. They release cytokines that enhance the immune response. Cytotoxic T cells, CD8+. These cells recognize and destroy virus-infected cells by binding to viral antigens presented on the surface of these cells. They release perforin and granzymes that induce apoptosis in the infected cells. Antibodies and their role. Antibodies, or immunoglobulins, play a crucial role in the immune response to viral infections. They are produced by B cells and have several functions. Neutralization. Antibodies bind to viruses, preventing them from attaching to and entering host cells. Opsonization. Antibodies coat the virus, making it easier for phagocytic cells to engulf and destroy it. Complement activation. Antibodies trigger the complement system, a series of proteins that enhance the immune response by promoting inflammation and assisting in the destruction of viruses. Formation of memory cells. After an infection is cleared, some B and T cells become memory cells. These cells remain in the body for years, ready to respond quickly if the same virus is encountered again. This memory response is faster and more efficient, providing long-term immunity against specific viral infections. Examples of viral infections and immune response. Let's examine how the immune system responds to two common viral infections. Influenza, flu. Initial response. The virus infects the respiratory tract, triggering the innate immune response. Interferons and NK cells help control the infection. Adaptive response. B cells produce antibodies specific to the flu virus. Cytotoxic T cells destroy infected cells. Memory formation. Memory B and T cells are formed, providing immunity against future infections with the same strain of the flu. Human immunodeficiency virus, HIV. Initial response. The virus infects CD4+ T cells, macrophages, and dendritic cells. The innate immune response is activated, but the virus evades many initial defenses. Adaptive response. The adaptive immune response is activated, but HIV targets and depletes CD4+ T cells, weakening the immune system over time. Memory formation. Although the immune system generates memory cells, HIV's high mutation rate allows it to evade immune detection, making it difficult to achieve long-term immunity without continuous treatment. The immune system's response to viral infections is a complex and highly coordinated process involving both the innate and adaptive immune systems. From the initial detection of viruses to the activation of immune cells and the production of antibodies, every step is crucial for effectively combating viral infections. Understanding these mechanisms helps us appreciate the incredible efficiency and adaptability of our immune system in protecting us from harmful viruses. In the next chapter, we will explore the role of vaccinations in enhancing the immune system's ability to fight infections. The role of vaccinations in enhancing the immune system. Vaccinations are one of the most effective ways to protect individuals and communities from infectious diseases. By stimulating the immune system to recognize and combat pathogens, vaccines have dramatically reduced the incidence of many serious illnesses. In this chapter, we will explore how vaccinations work, the different types of vaccines, and their impact on public health. Understanding vaccinations. Vaccinations introduce a weakened or inactivated form of a pathogen, or parts of it, into the body to stimulate an immune response without causing the disease. This exposure trains the immune system to recognize and fight the pathogen if encountered in the future. Mechanism of action. Vaccines contain antigens that mimic the pathogen. When introduced into the body, these antigens are recognized by the immune system, prompting the production of antibodies and the activation of immune cells. This process establishes immunological memory. Types of vaccines. There are several types of vaccines, each using a different approach to achieve immunity. Types of vaccines. Vaccines can be classified into several categories based on their composition and method of preparation. Live attenuated vaccines. These vaccines contain live pathogens that have been weakened so they cannot cause disease in healthy individuals. Examples include the measles, mumps, and rubella (MMR) vaccine and the chickenpox vaccine. Advantages: strong and long-lasting immune response. Disadvantages: not suitable for individuals with weakened immune systems. Inactivated vaccines. These vaccines contain pathogens that have been killed or inactivated so they cannot cause disease. Examples include the polio vaccine and the hepatitis A vaccine. Advantages: safe for individuals with weakened immune systems. Disadvantages: may require multiple doses to achieve full immunity. Subunit, recombinant, and conjugate vaccines. These vaccines use pieces of the pathogen, like proteins or sugars, to stimulate an immune response. Examples include the hepatitis B vaccine and the human papillomavirus (HPV) vaccine. Advantages: focuses the immune response on essential parts of the pathogen. Disadvantages: may require booster shots for long-term immunity. Toxoid vaccines. These vaccines contain inactivated toxins produced by the pathogen, rather than the pathogen itself. Examples include the diphtheria and tetanus vaccines. Advantages: induces immunity to the harmful effects of the toxin. Disadvantages: may require booster shots for long-term immunity. mRNA vaccines. These vaccines use messenger RNA to instruct cells to produce a protein that triggers an immune response. Examples include the Pfizer-BioNTech and Moderna COVID-19 vaccines. Advantages: rapid development and production. Disadvantages: requires careful storage and handling. The immune response to vaccination. Vaccination initiates a similar immune response to a natural infection, but without causing the disease. The process involves both the innate and adaptive immune systems. Innate immune response. When a vaccine is administered, the innate immune system recognizes the antigens and responds by activating immune cells and producing inflammatory molecules. This response helps to alert the adaptive immune system. Adaptive immune response. The adaptive immune system is activated, leading to the production of specific antibodies by B cells and the activation of T cells. Memory B and T cells are formed, providing long-term protection. Herd immunity. Herd immunity occurs when a large portion of a population becomes immune to a disease, making it spread from person to person unlikely. This indirect protection benefits those who cannot be vaccinated, such as individuals with weakened immune systems or allergies to vaccine components. Achieving herd immunity. Herd immunity can be achieved through widespread vaccination, reducing the overall number of susceptible individuals and thereby protecting the entire community. Importance of vaccination rates. High vaccination rates are crucial for maintaining herd immunity and preventing outbreaks. When vaccination rates drop, the risk of disease resurgence increases. The impact of vaccinations on public health. Vaccinations have had a profound impact on public health, reducing the incidence of many infectious diseases and preventing millions of deaths. Key achievements include eradication of smallpox. Smallpox was declared eradicated in 1980, following a successful global vaccination campaign. It is the only human disease to have been eradicated through vaccination. Reduction of polio cases. Polio cases have decreased by over 99% since the launch of the Global Polio Eradication Initiative in 1988. Efforts continue to eliminate the disease entirely. Control of measles, mumps, and rubella. The MMR vaccine has significantly reduced the incidence of these diseases, preventing complications and deaths. Impact on COVID-19. The rapid development and deployment of mRNA vaccines have been crucial in controlling the COVID-19 pandemic, reducing severe illness, hospitalizations, and deaths. Addressing vaccine hesitancy. Vaccine hesitancy, the reluctance or refusal to vaccinate despite the availability of vaccines, poses a significant challenge to public health. Addressing this issue involves public education, providing accurate information about the safety and effectiveness of vaccines. Addressing misinformation, combating myths and misinformation through reliable sources and scientific evidence. Building trust, engaging with communities to build trust in healthcare systems and vaccine providers. Policy measures, implementing policies that encourage vaccination while respecting individual rights. Future of vaccinations. The field of vaccinology continues to evolve, with ongoing research focused on developing new vaccines and improving existing ones. Areas of innovation include universal vaccines. efforts are underway to develop vaccines that provide broad protection against multiple strains of pathogens, such as universal flu vaccines. Personalized vaccines. Advances in genomics and immunology may lead to personalized vaccines tailored to an individual's genetic makeup and immune response. Vaccine delivery systems. Research is exploring new delivery methods, such as nasal sprays and skin patches, to improve vaccine administration and accessibility. Vaccinations are a cornerstone of public health, offering protection against a wide range of infectious diseases. By stimulating the immune system to recognize and combat pathogens, vaccines prevent illness, save lives, and contribute to the overall health and well-being of communities. Understanding the mechanisms, benefits, and challenges associated with vaccinations underscores their importance and highlights the need for continued research and public education. In the next chapter, we will explore ways to keep the immune system strong and healthy, including lifestyle choices, nutrition, and the role of supplements. Keeping your immune system strong and healthy. A strong immune system is essential for protecting the body against infections and diseases. While genetics play a role in immune function, lifestyle choices, nutrition, and certain supplements can significantly influence the strength and effectiveness of the immune system. In this chapter, we will explore various strategies to maintain and enhance immune health. The importance of a healthy lifestyle. A healthy lifestyle is the foundation of a strong immune system. Key components include regular physical activity, sufficient sleep, stress management, and avoiding harmful habits. Regular physical activity. Exercise boosts the immune system by promoting good circulation, which allows immune cells to move freely throughout the body and do their job effectively. Moderate exercise, such as walking, jogging, and cycling, can enhance immune function, whereas intense, prolonged exercise might temporarily suppress it. Sufficient sleep. Sleep is crucial for immune health. During sleep, the body repairs and regenerates cells, and the immune system releases cytokines, which are proteins that help fight infections and inflammation. Aim for 7-9 hours of quality sleep per night. Stress management. Chronic stress can weaken the immune system by producing cortisol, a hormone that suppresses immune function. Techniques such as meditation, yoga, deep breathing exercises, and hobbies can help reduce stress levels. Avoiding harmful habits. Smoking and excessive alcohol consumption can impair immune function. Quitting smoking and limiting alcohol intake can help maintain a healthy immune system. The role of nutrition in immune health. A balanced diet rich in essential nutrients supports immune function. Specific vitamins, minerals, and antioxidants play vital roles in maintaining a strong immune system. Vitamins and minerals. Key nutrients that support immune health include vitamin C, found in citrus fruits, strawberries, bell peppers, and broccoli. Vitamin C helps stimulate the production of white blood cells and acts as an antioxidant. Vitamin D, obtained from sunlight, fatty fish, and fortified foods. Vitamin D modulates the immune response and reduces inflammation. Vitamin E, present in nuts, seeds, and spinach. Vitamin E acts as an antioxidant and enhances immune function. Zinc, found in meat, shellfish, legumes, and seeds. Zinc is crucial for the development and function of immune cells. Selenium, found in nuts, seeds, and seafood. Selenium supports antioxidant defenses and immune function. Antioxidants. These compounds protect cells from damage caused by free radicals. Foods rich in antioxidants include fruits, vegetables, nuts, and seeds. Probiotics. Beneficial bacteria found in fermented foods like yogurt, kefir, sauerkraut, and kimchi. Probiotics support gut health, which is closely linked to immune function. The impact of hydration. Staying hydrated is essential for overall health, including immune function. Water helps in the production of lymph, a fluid that carries immune cells throughout the body. Daily water intake. Aim for at least 8 glasses of water per day. This amount can vary based on factors like activity level, climate, and overall health. Supplements for immune support. While a balanced diet is the best way to obtain essential nutrients, supplements can help fill gaps and support immune health. Some commonly used supplements include vitamin C. High doses can be taken during periods of illness to boost the immune response. Vitamin D. Supplementation is particularly important in areas with limited sunlight exposure. Zinc. Short-term use during the onset of symptoms can reduce the duration of colds. Probiotics. Supplements containing live beneficial bacteria can support gut health and immune function. Elderberry. This supplement is known for its antiviral properties and is commonly used to prevent and treat colds and flu. Echinacea. Often used to reduce the severity and duration of colds, although more research is needed to confirm its effectiveness. The role of a healthy gut. The gut microbiome, consisting of trillions of bacteria and other microorganisms, plays a critical role in immune health. A healthy gut microbiome supports the immune system by enhancing barrier function. A healthy gut lining prevents pathogens from entering the bloodstream. Producing short-chain fatty acids. These compounds support immune cell function and reduce inflammation. Modulating immune responses. Gut bacteria influence the activity of immune cells and the production of cytokines. Practical tips for immune health. Incorporating immune-boosting habits into your daily routine can make a significant difference. Here are some practical tips. Eat a balanced diet. Include a variety of fruits, vegetables, whole grains, lean proteins, and healthy fats in your diet. Exercise regularly. Aim for at least 150 minutes of moderate exercise or 75 minutes of vigorous exercise per week. Get enough sleep. Establish a regular sleep schedule and create a restful environment. Manage stress. Incorporate stress-reducing activities into your routine. Stay hydrated. Drink plenty of water throughout the day. Avoid smoking and limit alcohol. These habits can weaken the immune system. Wash your hands. Regular hand washing can prevent the spread of infections. Stay up to date with vaccinations. Follow recommended vaccination schedules to protect against preventable diseases. Monitoring and maintaining immune health. Regular checkups with a healthcare provider can help monitor and maintain immune health. Blood tests can assess levels of key nutrients and identify deficiencies that may need to be addressed. A strong immune system is vital for protecting the body against infections and diseases. By adopting a healthy lifestyle, maintaining a balanced diet, staying hydrated, and considering appropriate supplements, you can support and enhance your immune function. Understanding the factors that influence immune health empowers you to make informed choices and take proactive steps to stay healthy. In the final chapter, we will explore common misconceptions about the immune system and provide evidence-based answers to frequently asked questions. Common misconceptions about the immune system, evidence-based answers. 1. Misconception: the immune system is only active when you're sick. Reality: the immune system is constantly active, monitoring for potential threats even when you're healthy. It performs routine surveillance and maintains readiness to respond to infections or other threats at all times. 2. Misconception: taking high doses of vitamin C will prevent colds. Reality: while vitamin C is important for immune function, taking high doses has not been shown to prevent colds. It can, however, slightly reduce the duration and severity of symptoms if taken regularly before infection. 3. Misconception: you can boost your immune system with supplements. Reality: there is no scientific evidence that supplements can significantly enhance immune function beyond what is achieved through a balanced diet. Maintaining general health through nutrition, exercise, and sleep is more effective. 4. Misconception: all germs are bad and should be avoided. Reality: not all germs are harmful. Many are beneficial and help maintain a healthy balance in our microbiome. Good hygiene practices are important, but complete avoidance of all microorganisms is neither practical nor necessary. 5. Misconception: vaccines are not necessary if you're healthy. Reality: vaccines are crucial for everyone, regardless of health status. They protect against specific diseases and help build community immunity, which is essential for preventing outbreaks and protecting those who cannot be vaccinated. 6. Misconception: you can get the flu from the flu vaccine. Reality: the flu vaccine contains inactivated or weakened virus components that cannot cause the flu. Some people may experience mild symptoms, but these are not the flu. 7. Misconception: antibiotics are effective against viral infections. Reality: antibiotics target bacteria, not viruses. Viral infections, such as the common cold and flu, require antiviral treatments or supportive care rather than antibiotics. 8. Misconception: stress always suppresses the immune system. Reality: while chronic stress can weaken immune function, short-term stress can actually enhance immune responses. The impact of stress on immunity depends on its duration and severity. 9. Misconception: Eating sugar weakens your immune system. Reality: while excessive sugar consumption can contribute to overall poor health and may indirectly affect immune function, moderate sugar intake as part of a balanced diet does not have a direct, significant impact on immune strength. 10. Misconception: you don't need vaccines if you're young and healthy. Reality: vaccinations are important for everyone, regardless of age or health status, to protect against serious diseases and contribute to herd immunity. 11. Misconception: once you get a disease, you'll be immune for life. Reality: immunity can wane over time, and some diseases may require booster doses or revaccination to maintain protection. 12. Misconception: all vaccines cause side effects. Reality: most vaccine side effects are mild and temporary, such as soreness at the injection site. Serious side effects are rare and are outweighed by the benefits of vaccination. 13. Misconception: herbal remedies are always safer than pharmaceuticals for immune support. Reality: herbal remedies can interact with medications and may have side effects. It's important to use them under the guidance of a healthcare provider and not as a substitute for proven treatments. 14. Misconception: you only need to worry about your immune system when you're elderly. Reality: immune health is important at all ages. Children, adults, and the elderly all benefit from practices that support immune function. 15. Misconception: if you've had a vaccine, you don't need to worry about boosters. Reality: some vaccines require booster doses to maintain immunity over time, as immunity can diminish. 16. Misconception: washing your hands too often can weaken your immune system. Reality: regular hand washing is an effective way to prevent the spread of infections and does not weaken the immune system. It is crucial for hygiene and health. 17. Misconception: immune system disorders are rare and only affect a small percentage of people. Reality: immune system disorders, including autoimmune diseases and allergies, are more common than many realize and affect a significant portion of the population. 18. Misconception: you can tell if your immune system is weak just by how often you get sick. Reality: frequent illness may be due to various factors, including stress and exposure to pathogens. Immune function is complex and cannot be fully assessed by symptoms alone. 19. Misconception: more exercise always equals better immune function. Reality: while regular moderate exercise benefits the immune system, excessive exercise can actually impair immune function and increase the risk of illness. 20. Misconception: immune system health is not affected by diet. Reality: diet plays a crucial role in immune function. Nutrient deficiencies can impair immune responses, while a balanced diet supports overall immune health. Understanding these misconceptions and relying on evidence-based information helps in maintaining a healthy immune system and making informed health choices. If you enjoyed this video, please give it a thumbs up and hit that subscribe button for more exciting content. Your support means a lot to us and helps us bring you more videos like this.